So, all right, before we start 6.4, let's go back, right? Back in the day. Do you remember when you had, functions like this, like x squared plus 5x plus 6? And when we factored this, right, we got x plus 3, x plus 2, right? When we factor, what is it really that we're doing? We are coming up with one or with two or more simpler expressions, which when you multiply them, gives you this more complicated expression, right? So we are coming up with the simpler factors which multiply to that more complex expression, okay? Well, you know what? It turns out you can also do that not only with factors which multiply, but you can also do it with smaller expressions which may add up to a more complicated one, right? So just like we do that, what we're going to do in this section is we're going to come up with partial fractions, which means, right, you can, just like we can take a polynomial function and break it down into its factors, you can take a rational function and you can write it as the sum of two or more simpler rational functions. Okay, these functions will have real constants as numerators, and their denominators are, linear factors or irreducible quadratic factors. Okay, what does all that mean? Take a look at this example. Look at this rational expression here. You see that rational function? There used to be two simpler functions that when you added them up gave you that rational function. So in this lesson, what we're going to do is we're going to break that down into two or more simpler fractions that add up to that red one. The process by which we do this is called decomposition, right? So what you see here is that this fraction has been decomposed into two partial fractions. So this is called partial fraction decomposition, okay? It's a mouthful. All right, there are a few cases that you can run into with partial fraction decomposition, and we're going to take them case by case. Case one is if you have a denominator with linear factors, all right? So take a look at this one. Yes, this is the function from above, right? But we're going to see what the process was to get us there, okay? All right, so take a look at this. The first thing you want to do is you want to factor the denominator here. When you factor it, you get x minus 5, x plus 4. Do you see how the denominator here has linear factors, right? X minus 5 is a linear expression. X plus 4 is a linear expression. That's why this is the denominator with linear factors. Okay? So what we're going to do is we are going to decompose this into more fractions. How many terms are in the denominator here? Show me with your fingers. How many terms? 2 terms. That means we can decompose this into 2 fractions. Okay, so each one of them gets one of the factors. And now they need numerators. The numerators are going to be constants. So we just put constants there. We're going to go with A and B. It's customary to use capital letters. Okay? A and B. Okay, so now this is the framework with which we're going to work. So the process is that multiply through by the LCD, and then we're going to solve for A and B. Okay. The LCD here is the product of these factors. So it's x minus 5, x plus 4. So I multiply each of these terms by the LCD. After you do this step, your fractions should disappear completely, right? So here we get x plus 13 is equal to, the x minus 5 goes away, so it's a times x plus 4 plus b times x minus 5. Okay. Now I need to solve for a and b. Okay. There are many, many ways to do it. The way I like to do it is this. I like to plug in values into here, right? Plug in values for x. That will make one of the parentheses equal to 0. Okay, so let's do that. Let's plug in values of x to make parentheses equal to 0. I know that's not grammatically correct, but it's okay. Okay. So what can we plug in to make the first parenthesis equal to 0? X equal to what?
-4.
-4, right? X equal to -4. Okay, a little bit of background. Technically, you can plug in any number you want. You can plug in -54 for X. But it's more preferable to do it this way because then you have terms that just disappear, right? So when I do that, here I get -4 plus 13 equal to a times 0 plus b times this, -4 minus 5. So I get that 9 is equal to, that goes away, -9b. So b is equal to -1. Okay. Next, I do the same thing, but now I am going to plug in x equals 5 into the same purple equation and make the second parenthesis disappear. So when I plug in 5, I get 5 plus 13 equals to a times 5 plus 4 plus b times 0. 18 is 9a, a is 2. All right, so finally I can rewrite my original rational function, right? This is what I started with, right? I can say that this is equal to 2 fractions. The denominators are x minus 5 and x plus 4. And which variable belonged to the x minus 5? That was the a. So I put the 2 there. And the b, which is -1, I put here. Okay, but it's conventional to put the minus here and write it this way. Okay, so there we go. And now when you actually go and do LCD and you add up those two fractions with the blue and the red, you will get the bigger one that we started with. All right, question. The next, okay, well, so the next one we're gonna do is actually the same case, right? Where you have denominators with linear factors. But now, what if you have an improper fraction? Let's remind ourselves what an improper fraction is. It's when the numerator is bigger than the denominator, right? That's an improper fraction. Or it's when the numerator is equal to the denominator. Okay, so numerator and denominator are equal or the numerator is bigger. So these are both improper fractions, or when you have something like this, where they have the same degree. or if you have a higher degree in the numerator, right? That's an improper fraction. Okay, so if the numerator has a degree equal or greater than the denominator. When you do have an improper fraction, you first have to divide, you have to do polynomial long division, and then do the partial fraction decomposition. Okay, all right, so here, right, we have to use long division to rewrite the fraction. So notice here, this is an improper fraction. All right, let's do long division. Do you guys remember how to do long division from algebra 2? I skipped it this year. It would have been in chapter 2. Okay, so let's remind ourselves what the process is, right? You take the first term, divide it by the first term, negative 2x squared over x squared, and you get negative 2. You multiply the binomial with it, negative 2x squared plus 2x. And now you essentially have to subtract, right? What I like to do instead of subtracting, so instead of doing a minus b, I change the signs and add. That's just a trick that I like to do. So I change the signs and add, it's easier for me. 9 minus 2 is 7x. Okay, the minus 4 comes down. Oh, did they? What do you mean? Okay, just leave it. Sorry, we have a little bit of a construction and I guess they turned off the water. Okay, so how do you know you're done? When the degree here is less than the degree of the divisor, you know you're done. Okay, all right, so what is this now? This fraction now can be rewritten as negative 2, the quotient, plus 7x minus 4 over x squared minus 2x, x squared minus x. All right, so all this was from algebra 2. Okay, I've not really done anything. I've just rewritten it after I divided. Now what I'm going to do is I'm going to take this and decompose this. Okay, so what we're decomposing is 7x minus 4 over x squared minus x. And you know what? Do you mind if I just factor this out so there's less writing? X times x minus 1. Okay, underneath here I have 2 factors. So I need 2 fractions. X minus 1. A and B. And now the process is the same. Multiply by the LCD, x minus 1. This goes away. The x's go away. And the x minus 1's go away. So what I have left is 7x minus 4 equal to a x minus 1 plus b times x. Okay, next. What do we plug in? Well, first I'm going to plug in x equals 1. And I get 7 minus 4 equal to a times 0 plus b. So b is 3. And then to make this one go away, I plug in x equals 0. 0 is a number, remember? So I get 0 minus 4 equal to a times minus 1 plus b times 0. So negative 4 is negative a is 4. Okay, that means I can now rewrite my original fraction. What was the original fraction? It was negative 2x squared plus 9x minus 4 over x squared minus x. And now I'm saying this is equivalent to what I have found. Now, here is where you need to be super alert, because in the case of an improper fraction, remember how all this that I've done, it only represents the part in the black square. You still have this negative 2. So you need to include that negative 2 plus the decomposition that we just did, which was something over x plus something over x minus 1, right? And what goes over what? Well, x had the a, which is 4, and then 3 goes here. So that is the final answer.
Miss Maliki, really quickly, for the denominator for the first part, where you have x squared minus 4, should that be x squared minus x?
Oh, yeah. Sorry, I don't know where that came from. Okay.
I have a question.
Yes.
In the first problem,
Second case. The second case has a denominator with repeated linear factors. And for the repeated linear factors, you basically have to clone the denominators. I don't want to, before I confuse you, it's actually rather straightforward. Let me start with the example. Take a look at the example that I have here, right? Look at the denominator here. You have an x cubed, right? So it's the base of that is x, and the exponent is 3. Whatever the exponent is, you need 3 separate fractions for that one term. And the way you do it is, look, you do base to the power of 1, so x to the 1, x to the 2, x to the 3. You see that? So you build up to that. And then I have x minus 1 squared. The exponent is 2, so I need 2 fractions for it. And you start with the base with an exponent of 1, and you build up to your exponent of 2. Okay? So that's what you have to do. Let's take a look at, gosh, sorry. Let's take a look at this example here. So let's factor the denominator there by the time this loads. First, we need to factor out an x, right? So go ahead and factor out an x, and then you can continue factoring. So here, if I factor out an x, I get x squared minus 4x plus 4. So let me factor that a little bit further here. This is 3x squared minus 5x plus 4 all over x times. The other one factors as x minus 2 squared. Okay. Now, what are my factors in my denominator? I have an x, so I need 1 for that. Plus, now I have an x minus 2 squared. Because the exponent is 2, I'm going to need 2 fractions for it. And what I do is I start with the base with an exponent of 1, and I build up to the higher exponent of 2. Okay. Another way of taking a look at this is this. I have x to the 1 and then x minus 2 squared. If you add up all the exponents, it's 3. That's how many terms you need, 3 fractions. Okay? That's another way to check. Ben.
But for this one, I just don't get how, if there's 3 exponents, but there's like, okay, so x minus 2 comes up 3 times in the denominator, but it's only because there's the regular one and then it's squared in the other denominator. So why is it put twice instead of just x as denominator plus x minus 2 squared?
Because, like we said in the top example here, if you have a different exponent other than 1, so like this, in this case, it's x cubed. You have to start with that base to the power of 1, and then 2, and then 3, like, so basically build up. So here I have x minus 2 squared. The base is x minus 2. So I start with the base to the power of 1, and then build up x minus 2 squared, x minus 2 cubed, and so on. Okay? All right, now for the numerators, again, it's A, B, I need another one, C. You could go all the way to Z, right? But let's hope we're not going to get 26 terms, right? Okay, everything else is the same. So multiply everything by the LCD, which is x minus 2 squared. Okay, first term, everything goes away. So I just have the numerator, 3x squared minus 5x plus 4 equal to a times x minus 2 squared plus bx x minus 2 plus cx. Now, if I have 3 terms, that means I need to plug in numbers 3 times. Okay? So, first, let's plug in x equals 2. Okay? The first part gives me a 6 equal to a times 0 plus b times 2 times 0 plus c times 2. Okay, all these go away. So 6 is 2c, c is 3. Now I can plug in x equals 0 to make one of them go away. So I get 4 equal to a times negative 2 squared plus b times 0 times negative 2 plus c times 0. So 4 equals 4a, a is 1. Okay, I ran out of things that would make my terms equal to 0, but I still need to solve for b. So what now? Do I quit? No. Remember how initially I had told you, technically you can plug in whatever you want, but it's preferable to start with things that would make some of the terms equal to 0. Well, when you exhaust those options, just plug in anything your heart desires, 1,384, okay? Or let's plug in x equals 1, right? When you plug in x equals 1, you get 2 equals a times negative 1 squared plus b times negative 1 plus c times 1. Okay, 2 equals 1a minus b plus c. Oh, but wait, I know what a and c are, right? So 2 equals 1 minus b plus c is 3, b is 2. Okay? So what is this entire fraction equal to then, right? That big fraction was equal to this, was equal to something over x plus something over x minus 2 plus x minus 2 squared. And then, put in your A, B, C. So that's 1, B was 2, and 3. It's 1, 2, 3. Okay. All right, questions? Okay, last but not least, case number 3. When you have a denominator with prime quadratic factors. Okay, that means in the denominator you have a quadratic equation that you can't factor, a quadratic expression that you can't factor. Take a look at this one. What are my denominators? My terms of the denominator, x and x squared plus 1. Okay, x is fine, but the x squared plus 1, it's not linear anymore. Now it's quadratic, but you can't factor it any further, right? This means the numerator has to look different. So traditionally, I mean, not traditionally, technically, the numerator is always going to have one less degree than the denominator. So when our denominators were linear, x to the power of 1, the numerator was constant. Now, if this is a quadratic, the numerator has to be a linear factor, okay? Like mx plus b. You see how this looks like mx plus b? So it has to have that form. Okay, let's do this one, guys. So take a look at what you have. I have x cubed minus x over this. Okay. I have something to the power of 2. That means I need to have 2 fractions for this. The base is x squared minus 3. So I start with the base to the power of 1, and I build up to x squared minus 3 to the power of 2, right? I start increasing my exponents by 1 each time. Cool? Okay, now, this is a quadratic underneath. So the numerator has to have the form mx plus b, something else plus something. So I start with my first variable, ax plus b. The next one has to have the same form because it's also quadratic. But now where are we with the constants? I used ab. Next up is cx plus d. Okay? All right. Let's multiply by the LCD again. You know what? I'm going to save some ink here, right? We're going to multiply the whole thing by the LCD. First off, I get x cubed minus x equal to ax plus b times x squared minus 3 plus cx plus d. Everybody okay with this? Okay, now we're gonna FOIL this. So it's ax squared minus 3ax plus bx squared minus 3b plus cx plus d. Okay, this next step and on is my absolute favorite. Okay, absolute favorite. Okay, question. Yes, got it. Okay, now what we're going to do at this step is group by degrees of x. So write all of the x cubes together, the x squares, the x's, and the constants. So it means I get x cubed minus x is equal to ax cubed plus, let's put the x squares, it's only bx squared, minus everything with an x, so 3ax plus cx, and then the constants, minus 3b plus d. Right? Next, here's what we're going to do. X cubed minus x is equal to, okay, for the cubic term, I only have one term, so let's just copy it over. I only have one square term, let's copy it over. Here, we're going to factor out an x, but I want to put it at the end. So it's going to be plus negative 3a plus c times x. Okay, so I factored that to the right. And then plus, let's group these together because they're the constants. Okay, now here's what we're going to do. At this step, we're going to compare coefficients of like terms. And we're going to set them equal to each other. Malikan, what do you mean by that? That's just confusing. Here's what I mean by that. Look at the x cubed term here. And look at the x cubed term here. If the expression to the left and to the right are equal to each other, that means the coefficients of each of the terms have to be equal to each other. So if I have a 1x cubed here, that means this a also has to be 1, right? They have to have the same coefficient. So I say that 1 is equal to that a. Okay? Now let's move on to the square term. Where is the square term on the right side of the equation? I'm sorry, on the left side of the equation. There is none. That means it's 0. Okay? Next, the x term. This is the x's coefficient. And here, what is the coefficient of the x on the left-hand side? -1, right? So I say -1 is equal to -3a plus c. Can we actually solve that? We can, because this is -3 times 1 plus c. C is 2. Next, the constants. This is the constant. What is the constant to the left? What constant is there on the left side of the equation? 0. So I say -3b plus d is equal to 0. So -3 times 0 plus d is 0. So d is also 0. Okay, let's get back. What was the equation? What was the right-hand side? So I had x cubed minus x over x squared minus 3 squared is equal to, okay, ax plus b, right? So ax plus b, so what is our a here? 1x plus b is 0 over x squared minus 3 plus, I got x squared minus 3 squared. Now we have cx plus d. So c is 2, x plus what's d? 0. But of course, we can't write with the zeros, right? So this is x over x squared plus 3 minus 3 plus 2x over x squared minus 3 squared. Tell me that's not the most satisfying thing you've done. I mean, that's not the most satisfying thing you've done. I mean, it doesn't get much better, right?